All right, today we're going to talk about this idea of quantum suicide, quantum immortality. Should you commit quantum suicide? Now, the person who popularized this concept was an MIT physicist named Max Tegmark, and we're going to talk about all of the logical steps involved, and also along the way, we're going to learn a little bit about quantum mechanics. I'll keep it nice and easy for you. So, what is quantum mechanics fundamentally? As complicated as it sounds, it really is about one idea. And that idea is that infinity doesn't exist in the universe, and therefore infinite information cannot exist in the universe. And why does that matter? Well, the reason it matters is because if you're trying to figure out, for example, in an automobile accident, whether two cars came together at particular speeds and particular locations, well, that's an easy calculation for a physicist to do because these are very, very large objects. The problem is, the smaller the object, the more precise you have to be in the measurements involved, in its position, its velocity, and other characteristics. The problem is that infinite precision does not exist. There is no such thing as being able to locate anything, especially a proton, with perfect or infinite precision. That's just not possible because that information doesn't exist in the universe. So quantum mechanics is all about dealing with that inadequate information and ultimately how information gets added to the universe. It turns out that whenever quantum events happen, facts are added to the universe, and that is the source of new information in the universe. So it's really not that complicated. Now, the math involved can certainly be complicated, just as it can be difficult to calculate the exact measurements that you need or the exact trajectories you need to land an object on the moon, right? They're difficult calculations, but they're based on simple fundamental concepts. Same thing with quantum mechanics. So let me give you an example. Let's say you have two objects, object A and object B. And let's just say, for the sake of argument, that object B is moving toward A with this velocity. And velocity just means that it has a certain speed and the direction is in this toward A. And then let's also say that A is moving toward object B, maybe. So let's just say that A might be moving like that, or it might be moving like that. What do I mean by or it might be? Is it a lack of information? Yes, but not our own information. It's a lack of information in the universe. So this would be an example of where A is in a quantum state. I know, sounds spooky, but it's not. A is in a quantum state that is a superposition over these two possible trajectories. What is a superposition? Well, that's what quantum mechanics is largely about. A superposition exists when there is no fact of the matter embedded in the universe. So if there's no fact about whether the object is moving this way with this velocity or this way with this velocity, then it's in a superposition of being in both of those velocities. It's not in both of those velocities. It's not in one and it's not in the other. There's no fact about which velocity it's in or it has. But what can be said, A is not going this way. It's not going this way with that speed. That is what the superposition tells us. It also is not going like that. The example that I've given you, which is contrived, it's just an example, is where B is moving in this direction with certainty. And that's not realistic too, because again, that you can't have infinite precision there. But again, this is a really simple example where A is in a superposition of two possible trajectories and B is not in a superposition. I'm just keeping it really simple. So what can be said about A then is it's not moving this way, this way, this way, this way, this way. But the result of that, when you take away all the possibilities, it's not moving in any other possible trajectory, except you have not removed these two as possibilities, then what that means is that while there is a fact in the universe about A is not moving in those other directions or speeds, there is no fact about whether A is moving with this velocity or that velocity. And that's what a superposition is. A superposition exists exactly when there is no relevant fact about that object in superposition. I hope this should be super simple so far. This is quantum mechanics right here. And other than the math part, working through numbers, which you may or may not like, this is it. This just shows you that infinite information does not exist in the universe. So what that means is that there are cases where you just can't figure out information about a particle or an object or whatever, not because your measuring apparatus is inadequate, but because the universe itself doesn't know the answer to that question. That information is not embedded in the universe. So I'm giving you an example here, a contrived example, where it is true that B is moving in this direction with this speed, and that information is embedded in the universe. But there is no fact about whether A is moving like this or like this. Clear enough? So what ends up happening is, in the real world, if this were really happening, A and B have this trajectory. In one case, they will collide right there. Let's just say that if they were to collide, B would take, if this is the collision point, B would take that trajectory, and A would take this trajectory. The point is, in the first case, if A is realized in this direction, then there will be a collision between the two, and that collision results in their going off in opposite directions like this. So let's say hypothetically, although in reality, quantum mechanics would then tell us there are lots and lots of collision possibilities and those superposition states. We're not going to talk about that. We're just going to keep it very simple. So in case one, which is this, A has this, or is realized to have this trajectory, then a collision actually happens, causing them to go in these directions. If A is realized to have been going in this direction instead, you can see that A and B do not collide, and instead, A just continues on its merry way and B continues. That realization event is called, we can call lots of things, the reduction of the wave state, the collapse of the wave state. It doesn't matter. The point is, there is some event here where the universe decides, just makes a decision. Was A moving this way or was it moving this way? And that's when new information gets added to the universe. Now, for those of you watching at home, we're going to talk about MWI in just a moment. So that point, either the event or the non-event, either the impact or the non-impact, is the event that adds new information to the universe. The realization of one of these two possibilities. That's quantum mechanics. Now, there is something else I want to tell you about quantum mechanics. It's the idea of entanglement or correlation. So let's say that there's another object here, C, and it turns out that B and C have already interacted in the past. They already know where they are relative to each other. Now, I don't mean that objects or particles are conscious and they can know things, but rather, if it did think, then it would know where B is because of their past history together. Quantum entanglements are manifestations of past events. They are the embodiment of the history between objects. So let's say B and C are already entangled. Well, when this realization event happens, how does C know? Because this path is one that goes directly to impact C, whereas this one is not one that goes to impact C. So how does C know? Again, it's not conscious, but you get the idea. How does it know whether or not A is going to impact it, whether there's going to be a collision there? How does the universe figure that out? If the event happens here, or the lack of event happens here, how does the universe know whether or not there will be a collision between A and C, or there won't be? And the answer is entanglement. Universal entanglement. Essentially, every object, every particle in the entire universe is entangled directly or indirectly with essentially every other one, so that objects know how to interact with objects that they have not directly interacted with. So the universe will know whether or not there's going to be an impact between A and C. And there'll be a future to that. Either A will or won't impact C, and that is dependent upon whether or not A and B impacted, and that was dependent upon the resolution of this superposition state into one of those distinct alternatives. Does that make sense? That's literally, I have just shown you almost the entirety of the fundamental concepts of quantum mechanics just without the math. It really is not that complicated. There is simply not enough information in the universe to precisely specify anything. Locations, speeds, directions, charge, and so on. Okay, now, I said before that this event right here adds information to the universe, because before this happened, there was no fact about whether A was moving in either of those two trajectories. But after the fact, there is, and that's new information that gets added. Now, there are some physicists who will say, actually, the reverse has happened. You've reduced the amount of information in the universe because the superposition itself contained more information. I think that's patently false, but that's what some will say. And it doesn't really matter for the argument. So I've claimed that new information comes from that. And that's because there was a resolution, a collapse of this superposition into one of the distinct alternatives. Now, there are competing ideas or interpretations about quantum mechanics. Every one of them is indistinguishable from a scientific point of view, at least right now. So they're all making the exact same predictions. They're just different philosophical ways of thinking about them. And one of them I want to mention that's important for the idea of quantum suicide is the many worlds interpretation of quantum mechanics. And here's what it says. There is no new information here or change of information. Rather, what happens is at this event or lack of impact or whatever, the universe bifurcates. The universe splits into branches, one in which A is moving in this direction and impacts B and goes this way, and another in which A does not impact B, it's going in this direction and eventually impacts C. Both of those happen just in different branches or different universes. Now, I've argued in other seminars, you remember, why I and many people think that this is non-scientific. It's not even a hypothesis if it can't be rigorously tested by scientific inquiry. Nevertheless, we need this interpretation to talk about and to come to conclusions about quantum suicide, which is taken seriously by Max Tegmark, Sean Carroll, and lots of physicists. So somebody who believes in the many worlds interpretation of quantum mechanics would say that because both of these possibilities happen in different universes, they are equally real from the perspective of any observers. So the universe splits at this moment, and I happen to be witnessing this or thinking about this or whatever. And so in one universe, I observe that A has collided with B and does not collide with C. And in another universe, I observe that A collides with C and not with B. So what they would say is there's really no new information that happens here, but rather the information quantity of the universe in the form of what they would call the universal wave state remains constant. And so whenever it appears like one of these things happens, a resolution of a superposition into one of the distinct alternatives, then there's no new information, but rather there are just different observers in those different universes coming to different conclusions. Now is where we talk about quantum suicide. So the notion of quantum suicide was initially talked about, I believe, by Hugh Everett in the 50s, but was made popular by Tegmark in the late 90s and early 2000s. And so it goes like this. Imagine there is a quantum gun. And what I mean by a quantum gun is it's designed so that when you pull the trigger of the gun, a bullet will explode out the barrel dependent on the resolution of a quantum event. So let's say that that event is a binary, meaning there's two outcomes, just like I gave in the last example. In reality, the vast majority of quantum superpositions they have a huge number of dimensions, as a physicist would say. There's a huge number of distinct orthogonal outcomes. But let's say in this case, there's just two possible outcomes. And an easy way to do that is with a spin measurement. So the spin of an electron, for example, can be measured in a particular way, and that result will either be, say, up or down or left or right. It'll be a binary outcome. And you can create binary outcomes in quantum events and create superpositions of binary outputs. So let's say it's designed so that the gun itself is designed so that when you pull the trigger, the first thing that happens is a quantum measurement event occurs on a quantum object that is in superposition over states, say A and B. I don't know what they are. Again, it's binary. I'm just making this up. Could be up or down, could be red or blue, whatever. And if the outcome is A, then the gun doesn't fire. You pull the trigger, but just nothing happens. And if the outcome is B, then the gun fires. Now, the question is, what happens if you stand in front of a quantum gun? Let's say your lab assistant is holding the gun, and I understand this is a macabre example, but this was the example of Max Tegmark. So if you're standing in the lab with your lab assistant holding this quantum gun toward you, what happens when the lab assistant pulls the trigger? Let's just say that the quantum event is such that, and I'm going to be very simple here. I'm going to call this state A. This is Brockett notation in quantum mechanics. The idea is that the gun being in state A is one where the measurement event resulted in an A outcome and he did not fire a bullet. And then the state B is just the opposite, where the quantum event is measured as B and the bullet does emerge from the gun. So let's say that the state of the gun immediately after it's fired is going to look like, this is pretty much the most math you're going to see in this whole seminar. All this says is that this is a superposition state of the gun immediately after it's fired. And A and B are constants. They turn out to be complex constants. And the idea is that the likelihood of measuring outcome A, where there's no bullet, this is called the Born rule. That outcome has a likelihood of the magnitude of A squared, and then the likelihood of B happening is the magnitude of B squared. Now, if you don't know math or like math, just forget about that. The point is, these tell you something about the relative probabilities of these two events happening. So I'm going to make this real easy. I'm just going to say that let's just choose the gun so that there's a 50-50 chance of each one happening, like a flip of a coin, okay? You know, A and B are the same here. I'm just going to use this and just forget about the constants for the moment. We're just going to say that the likelihood of A and B being measured are equal. After the gun and any potential bullet have an opportunity to interact with whoever's on the other side of that gun, here's what it looks like. Let's say it's Dr. Tegmark doing the quantum suicide event. So we'll just say the initial state of the gun, just a very general symbol to represent the state of the gun, and together with that of Tegmark. After the assistant pulls the trigger, then this state becomes, it's just going to be that outcome A where Tegmark is alive because there's no bullet. So I'll say alive here. And what I mean by this is a state of Dr. Tegmark being alive and a state in which he is dead. Now, what I've left out of here, of course, were those constants, but because we've said that they're equally likely, we're just going to make this very simple. Now, according to a collapse interpretation of quantum mechanics, when this happens immediately, whether by spontaneous collapse or some other means, one of these happens with the probability determined by these constants. So after the gun is fired, either a bullet didn't come out and he's alive, or it did come out and he's dead. But MWI, which Tegmark subscribes to, says, no. Nothing happens. That is the state. There's no change in information. There's no fact about whether the bullet did not come out or did come out. But rather, we would observe branches of universes or new universes in which one happens and the other happens. Tegmark then makes this argument. He says, if I do this experiment, and it easily could be done, if he does that, what will he experience? Well, his argument is that since any branch of the universe in which he's not alive is one in which he's not conscious and can't observe the outcome, then the only branches that he's conscious and aware in are the ones in which no bullet came out of the gun. So what he argues then is that his lab assistant could shoot the gun once and he would be guaranteed to say, well, I'm still alive. The lab assistant could do it again and again and again and again and again and again, as many times as he wants. And according to this argument, if there is no collapse of this into one of these two states, then, according to Tegmark, he is guaranteed to be alive and be conscious because the only universes in which he could make the observation that he's alive and conscious are the ones in which this result happened. So that is the idea of quantum suicide. And another way of thinking of it is quantum immortality, this idea that according to him, he can have the lab assistant shoot the gun as many times as he wants, and Tegmark will still be alive. Now, From the other side, from the perspective of the lab assistant shoots, pulls the trigger, and on the very first try, he may see a bullet emerge and Tegmark die. And if it didn't happen on the first time, with a 50-50 chance, it'll happen on the second time. Even if it doesn't happen on the second time, on the third time, there's a 50-50 chance. What's the likelihood of doing it 100 times in a row and seeing Tegmark survive because no bullet was ever fired? Well, again, if the probability is such that the magnitude of this squared is 1/2, 50-50, then the probability of surviving 100 times, or 100 pulls of the trigger, would just be 1/2 to the power of 100. It's a really, really small number. And the point is, you could just continue firing the gun as many times as you like, and Tegmark claims that he will always survive it because the only universes that contain a Tegmark that can observe that he survived are the ones in which no bullet was fired. Kind of strange, right? Okay, so this is a strange argument, but it is actually believed by a lot of smart people. So let's analyze it. Notice that the entire argument depends on two assumptions. We'll call them assumption 1 and assumption 2. Assumption 1 is the assumption that MWI is correct. Now, of course, I told you that right now, MWI is an interpretation of quantum mechanics that is indistinguishable from other interpretations because it gives the same empirical results. However, there have been people who propose ways to empirically distinguish MWI as an interpretation to see if it's actually a theory. Nevertheless, it assumes that MWI is correct. And then the second thing it assumes is that physical death results in the eternal end to consciousness. So let me talk about A2 for just a second. This is assumed by so many physicists and scientists in general. It's just unbelievable, and they often don't even state that assumption or realize that it is an assumption at all. You have to assume that the physical death, once the brain is dead or the body is dead or something, results in eternal cessation of consciousness. Otherwise, this argument simply doesn't work, right? Is there an afterlife? Now, you remember from the seminar on whether or not there's any scientific evidence for an afterlife. In that earlier one, I talked about this belief that consciousness is entirely produced by the body or the brain. So why does anyone believe this statement, this assumption 2? The reason people believe it is because of that underlying assumption that consciousness is entirely produced by the brain/body. If this is true, that's true. Right? And that's what most scientists and physicists believe, although they often don't state what their reasons for that are. So in that seminar on an afterlife, I explained to you why this belief is unfounded in science. And in fact, in another seminar, I proved to you why this is in fact false. So if this is false, then there might not be any good reason to believe assumption 2 at all, that one's conscious awareness or conscious identity may persist after the death of the body or the brain. I gave some reasons, some scientific reasons to think that that could be true. It's not a slam dunk in terms of proof, absolutely not. And you can't come to that question with your preconceived notions about what you want to be the case, but rather the point of that seminar was simply to show that this assumption, which is false, is what supports this common belief. So if this is false, and this is implied from this, now this still in fact may be true, even if the statement is false. But the reason that most people think that this is true is because of this often hidden assumption, and this is false. So that's A2. So already I'm very skeptical of quantum suicide because A2 may not be true, and there may not be good scientific basis for believing it. But now let's look at assumption 1. The problem with assumption 1 is that it doesn't account for conscious identity. Let me show you what I mean. Let's change the experiment just slightly so that maybe instead of a gun that shoots a bullet, maybe it's something that instead causes some sort of pain. So here's, this state would be alive, feeling no pain. This state would now be alive, but feeling pain. Maybe the bullet just grazed his ear, didn't kill him, but caused him pain. Something like that. You get the point. So that in both cases now, Tegmark is actually alive. How does that change things? Let's look at the before and after state. So before, Tegmark is just thinking about, okay, this is kind of a weird experiment, but I want to prove it to the world. So he's just standing there waiting for it to happen. And the question is, what does he experience? There's only a few possibilities. So what does Tegmark experience in this case? Now, he's already admitted that he asserts that when this is dead, he experiences alive. Before the trigger is pulled, he's thinking about the experiment. And then after the trigger is pulled, he is still standing there and saying, look, I told you so, MWI is correct. He's saying that to his lab assistant, right? It's still him. So he agrees that his conscious identity will flow from that before to that after version of himself. But now with MWI, in some sense, they both occur, but in separate worlds. So the question is, what does that Tegmark experience before and after the trigger is pulled? There's only going to be three possibilities. One is neither. Well, so he doesn't experience anything at all, would be that first option. Right after the trigger is pulled, there is no conscious awareness or conscious identity at all. Well, that can't be right? Because if he's conscious, if he has a conscious identity then why would it be that after pulling the trigger, there is no conscious identity whatsoever? The second possibility is both. Now, if you remember the seminar on why computers will never be conscious, you're going to see this very similar line of argumentation, reasoning. The second possibility is that he actually experiences both, being alive without pain and being alive but with pain in separate universes. But I explained in that other seminar how that violates special relativity. Because the Tegmark who is alive and not experiencing pain, in order for him to also experience this in some separate universe would require superluminal information transfer. It just can't happen. He can't experience both of them. And then the last possibility is one or the other. Because these are both sort of nonsense, this is often the reply. Well, he experiences no pain, but there's another Tegmark in a different branching or a different universe that does experience pain. The problem with that is that if his identity flows into this one and not this one, then that must mean that there's something physical that causes the differentiation, that causes the choice. But that can't be the case because right before it was the same universe, and so these two are otherwise exactly identical. So there can't be anything physical that chooses between these two possibilities, and therefore, it can't be one or the other. But these are the only possibilities. What that means is that the original assumption that this is the evolution of the wave state is false. Nevertheless, despite that there isn't good scientific evidence to support this statement, and that this may in fact be logically false, Tegmark believes them, other people believe them. So, what should Tegmark do if in fact he believes both of these with certainty or near certainty? How should he use that information? Well, here's one possibility. So what he does is he goes to an insurance company and he says, we're going to do this quantum suicide experiment. And he says, I'm going to have my assistant pull the trigger 100 times in a row. Now, if the likelihood of each of those events is a half, then the likelihood of him surviving from the perspective of the insurance company after 100 pulls of the trigger is about equal to the likelihood of him surviving is a massively small number. The reciprocal of this is 10 and 30. That's 1,000,000 trillion trillion. So here's what he says to the insurance company. I'm going to buy a life insurance policy from you. I'm going to give you $1. Now, fair odds for me surviving 100 pulls of the trigger of the quantum gun would pay out 10 to the 30th dollars, 1,000,000 trillion trillion dollars. Now, that doesn't even exist. But he tells the insurance company, look, I'm going to give you an amazing deal. I'm going to accept an insurance contract for much, 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 much less than that. Let's say $1 billion? Just $1 billion is all, okay? So 1 billion has 9 zeros. This has 30. So we're way, way off. So the insurance company should jump at it, right? I mean, yeah, it's not much. They're not getting much, just $1. But they know with certainty, absolute certainty, well, this amount of certainty that he's going to die and that there will be no payout. So it's kind of a reverse life insurance policy. The idea being that if he survives this crazy stunt, he gets $1 billion. If he doesn't survive, they just keep his $1. That is the insurance deal. It's a great deal for an insurance company because their likelihood of payout is so unbelievably low that really, mathematically, they could afford to pay out much, much, much more than this in the case of his living because he's not going to live. There's no way he's going to live, right? There is some insurance company or some corrupt gambler or some bookie somewhere who would be willing to give payouts like this. I mean, even if it's not $1, nobody's interested in $1. How about say, I'm going to give you $10,000 for the policy, but if I win, if I'm still alive after those 100 pulls of the trigger, you give me $1 billion or even 10 million, right? Mathematically, it would be a great deal for any gambler who took this bet. And yet, quantum suicide or quantum immortality guarantees, according to Tegmark, that he is going to survive and to collect that $1 billion or 100 or $10 million. Now, there's a lot of great things that can be done with a lot of money. You can invest this in clean water supplies around the world. You can invest this in finding vaccines for diseases or funding treatments or funding lower cost medications around the world. There's so many good things you could do with a ton of money, right? If you were a philanthropist. So let's just assume that Tegmark is a philanthropist, that he just doesn't want $1 billion for himself. Although it's fine if he does, but the point is, whatever it is that he values in the world, there's a really, really good chance that $1 billion would make a pretty good impact, right? What about this? What about if he doesn't even want money? What if he wants to win the Nobel Prize in physics by proving that MWI is correct? And the way he does it, again, is by doing this experiment. He says, look, physicists, look, world, I'm going to prove that this is correct by standing in front of my assistant and having him pull the trigger 100 times. Oh, that won't convince you? 1,000 times. Well, here's the thing. According to Tegmark, he will be alive and conscious. His conscious identity will flow to that one case in all the trillions and trillions of them in which he is alive and conscious. And the world around him will be indistinguishable in essentially every other way from every other universe, except that in that one he's alive, and everyone else around him saw this amazing feat, this amazing achievement of him getting shot by a quantum gun 100 times in a row. And according to MWI, all of those people, his spouse, his children, his friends, his colleagues, will be indistinguishable to him from those other worlds. They will be very, very real, according to MWI. So all those people are going to congratulate him, say, I can't believe it. You're exactly right. MWI is correct. You win the Nobel Prize. And because you made that insurance contract before, here's $1 billion to do whatever you want with it. Wouldn't he do that? Wouldn't anybody do that? So if you start with these two premises and you believe them firmly, I'm absolutely certain that MWI is correct. I'm absolutely certain that physical death results in the eternal loss of consciousness. If you were sure about those two things, and demonstrating this quantum immortality would be hugely profitable or beneficial. If you take these things together, what's the result? The result is you better do it. You better go ahead and do this. Well, make sure you set up your insurance contract first. Make sure you have witnesses for this event first. But you better do it, because you will then be in a world in which you have survived the pull of the trigger of a quantum gun 100 times or 1,000 times or whatever. And that will bring notoriety and money and whatever it is that you're seeking. So should Tegmark do this based on these assumptions? And the answer is, well, obviously, yes. Max Tegmark should commit quantum suicide. But here's the thing. He's a smart guy. He knows this. I don't remember seeing anything that he wrote that suggests that he knows this point, but come on. He's a smart guy. He knows it. So why hasn't he done it? In other words, why don't we right now live in a world in which he has already done this? The fact that he has not yet done this, the fact that we don't live in a world in which either he's dead from a gunshot wound from a quantum gun, or in which he has tons of money from an insurance contract or has won the Nobel Prize in physics, because we don't live in one of those worlds, we know that he hasn't done this. What that tells me is that he's just not all that confident, even though he says he is quite confident in MWI. I don't think he is that confident. And I think that when most physicists who claim to believe this with certainty, when it's put to the test, they back away. Their logic doesn't hold, and that's because they don't actually believe the assumptions. The last thing I want to mention is that there's a lot of talk here about this quantum gun, which seems like just kind of this abstract idea. You'd have to build it in a lab. It's a really weird thing. It's actually far easier than you might imagine. And that is because, as it turns out, every truly random event in the universe is the result of a highly amplified quantum event. I call those a highly amplified quantum event. So when you're sitting at the roulette table at a casino, when the ball spins around, there is determinism involved. But after a certain point, it becomes truly unpredictable because random quantum events become the things that dominate where that ball is going to land. The amplification has to do with chaos, nonlinear changes in the future due to these quantum events. So really, to do the quantum suicide, you don't even need anything complicated, a quantum gun. Really, what you could do, what Tegmark could do, would be to sit at an actual casino, put all his money on red, as long as he has somebody with him who has a gun, maybe it's hidden, right, because they're in a casino, and he's ready to shoot Tegmark if the result is black, right, because there are 3 colors in roulette: red, black, and green, the 0 and the double 0. So maybe I'll just say, if the outcome is not red, then the person kills Tegmark. And Tegmark can't be watching. So all he does is, he's sitting at the roulette table, he puts money on red, all his money on red, turns away, and just waits. Maybe putting in earplugs, so he doesn't want to hear the croupier say what color it is. So he just waits. If the outcome is not red, his assistant kills him. Otherwise, doesn't kill him. Again, because those highly amplified quantum events are what cause the randomness in the world, that roulette ball, the outcome, whether it's red or not red, is in fact the result of a quantum event, at least one. And so that implies you need some complicated quantum to do this experiment. All you have to do is on a true random event in the world casino, and the exact same of all the people who believe, all the physicists who firmly believe this with certainty and firmly believe this with certainty, and should obviously believe this because that's common sense. How many of them have attempted quantum suicide? 0. Why? I think because they love arguing this stuff because it's interesting, but in reality, they don't really believe it. That's fine. They shouldn't believe it because I think there's a good chance that this is logically false and there's no good scientific evidence, direct or indirect, to support that claim. Cool, right? Interesting.